Breaking boards, oh yes. Suppose I take a pine board, and my goal is to break it. Well, to break it, you have to apply a force to it. If I take this pine board, and I support it on the ends, and I push in the center, what will happen is the board will deflect. And then at some point, the board will break. The board will break. And so I get something like this. I push on it, the board deflects, and at some point it breaks. It works like a spring, actually. And if you look at the force that it takes versus the deflection of the board, we get a graph that looks like this. Force versus deflection, it's a straight line. That's the same thing we'd get for a spring, okay? As you do that, as you push on the board, it's bending, force is increasing, you're storing energy in the board. What form of energy do you have in the board? What kind of potential? Spring potential energy. You're putting spring potential energy into it. Now, here's the thing. If my goal is to break a board, if I take this board and I set it up on blocks like so, and I'm just going to try to push on it and break it, I can't push with a force of 800 newtons. I can't push. I don't weigh 800 newtons, okay? I'd end up doing a handstand, and it would be and it wouldn't go. It wouldn't go. So I can't stand on this board and break it. So if I'm going to break it, I have to do something else. What I'll do is do a collision. So I'm going to do a collision with the board. Oh, yes. Get your hand moving fast, hit the board, then you can break it. But you got to be sure that you have enough energy to make this happen. So if you're going to break a board by hitting it with your hand, you got to make sure that your hand has enough of what kind of energy? Kinetic, to come in and provide the potential energy necessary to break the board. And that's ultimately, this is a collision problem, and it's an energy problem. Now there's another calculation which you need to know, and that's this. It takes 800 newtons to break the board. You probably want to know how much force does it take to break your hand. And the answer is a lot more than this. Maybe 12, 20,000, something like that, newtons, way more than this. So you have a lot of cushion here. The board will break long before your hand does. And so in terms of the force, this is safe. As long as your hand is moving fast enough, you're able to do this. By the way, I will mention, just because it doesn't break your hand, that doesn't mean that it doesn't hurt. It hurts a lot, and you can damage yourself this way, okay? So I'm a trained professional, but don't go home and try this, okay? But let's do this calculation. How fast would my hand have to be moving? I want to do this. I'm going to bring my hand down, moving fast, and I want it to go through the board. How fast will it have to move? My hand has what kind of energy? Kinetic, and it goes into spring potential energy, elastic potential energy. Could we say, if I just cut to the chase, the kinetic energy of my hand better be equal to the spring potential energy in the board when it breaks? So can I say 1/2 mv squared is equal to 1/2 kx squared? I think so. What are we missing in this equation? Okay, what's the spring constant? You don't buy it like that at Home Depot. You don't buy it by spring constant. Okay, but we can calculate it because we've got data right here. And our data says when you apply an 800 Newton force, it deflects by 1.2 centimeters. And I can do this equation. I can do the spring stretch equation. F is equal to K times X. What's the force? 800 newtons. What is X? 1.2 centimeters, 0.012 meters. And so I can calculate the spring constant. It's just 800 newtons divided by 0.012 meters. And so I end up with the spring constant of 6.7 times 10 to the 4th Newton meters. So then I can work out this. I can work out 1/2 kx squared. 1/2 kx squared is 1/2 times 6.7 times 10 to the 4th Newton meters, newtons per meter, sorry, not Newton meters, newtons per meter, times 0.012 meters squared. So I end up with an energy of 4.8 Newton meters, or 4.8 joules. So how much kinetic energy does my hand have to break the board? 4.8 joules. Oh, and we can work out what speed that corresponds to. 1/2 mv squared is equal to 4.8 joules. I'm going to assume my hand has a mass of about 1/2 kilogram. I'm built pretty light. So I end up with this. I can calculate. I put in like 0.5 kilograms. And I can calculate V. And if I do it, I get a speed of 4.4 meters per second. Approximately how many miles per hour is that? 10. It's about 10 miles per hour in round figures. Do you think I can move my hand at 10 miles per hour? Yes. Yeah. I mean, I can run at 10 miles per hour. So I could go like this, whee, and I could hit the board as I go by, and it would break. My hand would go through it. Seriously, I'd have enough energy to do this. And there would be a collision, and the force is large enough, and the energy is large enough. Everything is going to break. Everything is going to break. Now, you can also break bricks. As a matter of fact, if I were to break this brick, here's your equation for it. It's the same thing. Bricks take more force to break, but they take less, they won't flex as far. And the energy required to break this brick is about the same as the energy required to break the board. Okay? So I could stack up bricks and break them. Here's the thing, though. Same amount of energy. So if I can break a board, I can break a brick. But the amount of force necessary to break the brick, very close to what's required to break your hand. Okay? And so this is, yeah, not so good, not so good. In fact, if you're going to break bricks, you want to take some precautions to do that. You could use a little bit of cushioning in order to kind of make that more comfortable. Now, a while back, somebody brought me a motivational video about breaking boards and or breaking blocks and other kinds of things. And this is a way of kind of like proving what you're capable of, etc. And to steel myself up for like breaking boards in front of a room full of people, I want to watch this, and I'll invite you to watch this with me, this motivational video, to kind of like get steeled up for this. Here we go.
This man has tremendous power and trying to drive his fist through 12 concrete slabs at once with his fists. Ladies and gentlemen, Don Smith from Baton Rouge, Louisiana. Fire up, Don, fire up! Pump those arms up, Don, pump them up. Get them together. Get them together, Don. They gotta be together. Drop your hips. Drop your hips. They gotta be together.
All right, my turn. And I think I got a couple of pointers here that I can apply. So let's see. What? Drop the hips? Is that what I'm supposed to be doing? And I'm doing this? Oh, wait. There was more, wasn't there? Wait a minute. Hang on. Oh, yeah. Okay, here we go. And then I just have to get my hand moving fast, right? And we're breaking one board. Not so bad, actually. All right. Now, wouldn't it be more impressive to break a stack of 5 boards? Yeah? Oh, yeah. And I'm going to do that. And if you want to do 5, here's what you do. You put spacers between it. Did you notice that the blocks he was breaking had spacers between them? And then if you do that, it's not like breaking 5 boards. It's like breaking one board 5 times, which is much easier. Except it's actually easier than that, because when I bend the board, the energy goes into the form of elastic potential energy, and when it splits, some of it comes back again. Oh, yeah. And it goes into kinetic energy. And so if you can break the top few, they'll be moving fast enough to help you break the bottom ones. And so breaking 5 shouldn't be too much harder than breaking 1. And actually, it's a bit harder, and it hurts more. And this really is something. Okay, so here we go. Ready? Dropping the hips. Working it. Here we go. And 1, 2, and... Oh, yeah. Oh, gosh. Now, that brings us back to this whole idea of the remarkable things that your body is capable of.